All right. So hello, everyone. I'm Javier Gavilanes from Sigma Cognition. We are a Spanish company that's focused on artificial intelligence solutions. And I'm going to talk about, sorry, let me see how this works. Yeah. I'm going to talk about the work that we did for the DigiEcoQuarry project. I'll describe the data warehouse, a storage solution that we are using for the data that the AI services consume, and then I will describe the different AI services. I'll describe the first four, and then José Luis Blanco will continue with the last two. Just to mention that all these services have been developed in cooperation with the UPM AI team and have been deployed in at least one of the quarries of the project. So starting with the data warehouse is a central repository that's focused on storing business information. It integrates data from different sources, although it's basically or mainly used in conjunction with a data lake, where all the raw data is stored in the project, the data lake that was described by Sadek. But it also integrates data from additional sources that we see when we talk about the forecast service, sorry. The information in the data warehouse has to be organized and structured in a way that's appropriate, either to be consumed by the AI services or to be directly visualized in Power BI. So we had to create a series of data processing pipelines that do exactly that. They take the data from any source, from the data lake or whatever, and give it a structure, create a table, and stores it in the data warehouse itself. As a storage solution, we used Google BigQuery. And as I mentioned, some of this information is directly visualized, which is done through Power BI, for which BigQuery has a native integration. So visualizing that data from Power BI, it's quite easy. Having talked about the data warehouse, I can go into the AI services themselves, starting with the quality determination service. This service has been deployed in CEMEX, in Valdilecha, in Madrid, in the quarry they have in this town nearby Madrid. And it's focused on analyzing the material that enters, the quality of the material that enters the quarry. This is done by looking at both the crusher and the C3 belt, which carries the waste material, and together, looking at this crusher and this belt, we see all the material that enters the plant. It has two main parts then. So the first one on the crusher, and the goal of the service is to analyze its occupation, so how full the crusher is, and to detect any oversized fragment, any fragment that's going to be too big for the crusher to be processed. And in the C3 belt, it also analyzes its occupation and the percentage of clay versus limestone of the material that's going through the belt at any given point. And it also analyzes or deducts the color code, the Mansell color code of the material that's going through this belt. In the picture, you will see number one represents or shows the camera that's looking at the crusher. And in number two, we see the C3 belt, the waste belt that I was talking about, together with the camera looking at this belt and a LED array to light this belt because it's covered. We need external lighting. And also part of the project is a computer that receives the images captured by these cameras and an antenna that helps sending these images out of the quarry to our premises via 5G connection, 4-5G connection. Looking a bit more deep how this service works, the process starts with a data set of images that they are captured every 5 minutes, although this time can be easily adjusted. Right now, I think we are getting them every 5 minutes. And we need to obtain a segmented mask. The process to obtain this segmented mask starts. First of all, we need to address the variability of the background, because due to the varying lighting conditions, the background changes a lot throughout the day. So for that, we do a normalization process, a conversion to grayscale, and so on. Once this background normalization is done, we need to remove the background. For that, we are using, first we tried some traditional methods, such as median or K9 neighbors, which proved to be not very appropriate for this task. And we ended up training a variational autoencoder that takes as input one of these images, and the output is an image, only a background image, sorry. Now, doing the difference between the input and the output image, we will obtain only the foreground objects. Once we have the foreground objects identified, we need to segment the image in order to identify or to select each of the rock fragments. For that, we did it using a UNet network, which is a fully convolutional network that's widely used in this type of task. And this network was trained first with the help of the SAM model, the segment anything model by Meta, which was then fine-tuned by manually, thanks to manual annotations done by our human annotators team in Sigma. So at the end, we obtained this segmentation mask that now can be analyzed by a series of processing scripts that are going to deduce, on one hand, the occupation of the belt, and on the other hand, to detect one of these oversized rocks that I was talking about. And this information is now displayed in Power BI and through this dashboard that we see here. And we see the information that I was talking, the blue line. Sorry. The blue line represents the occupation of the cluster at any given point. We can also see the threshold here to see if all the occupation is below the acceptable level. And if one of these oversized fragments is detected, the number becomes red to give an indication that a potential issue can occur. And this dashboard can be filtered by time to focus it on a specific moment in time. So that was the first part of the quality determination service. The second part, which is focused on the waste belt or the C3 belt, I won't go into as much detail as before, but the process is similar. It starts with a data set of daily images, which are then processed as segmented to obtain the segmentation mask that can be later analyzed by the processing scripts. In this case, we obtain both for limestone and for clay the occupation. This time it's separated by the two different types of materials, and the colorimetry, which is the monthly color code of both the limestone and the clay. And again, as before, this information is displayed through the dashboard, where we can see now the occupation here also divided by clay in red and by limestone in brown. We also see the color code of the material, as I mentioned before. This is the monthly color code for limestone and clay. We provide also as a convenient information the weather report for that day and access to the history weather report. And as before, the graph or the dashboard can be filtered to focus it on a specific moment in time. Okay, so that was the quality service. Now the grain size determination service. This one has the goal of analyzing the size distribution of the material as it goes through the C33 belt. Sorry, this is an end product, and the material is the 420, which goes from 4 to 20 millimeters. And yeah, the service aims at determining what the distribution of sizes of this material. Going a bit into the details, as before, the process starts with the data set of daily images. Then they are segmented. This segmentation is done by manually annotating this type of image, which, as you can see, is not an easy task. And once we have the segmented image, we go and analyze its size. For this size analysis, we followed different strategies. We are measuring on one hand the area. We are also measuring the shortest side and the longest side. And with this data, we are again generating daily results that are stored as before, which I didn't mention, but that are stored in the data warehouse and visualized from Power BI. In this case, we are also analyzing any potential anomalous event, so to say. So whenever we find that too much material is in the size range of over 25 millimeters or over 40 millimeters, we generate an event. Here it's important to mention one issue with this type of service is the occlusion. Because of the nature of the project of the service, the camera can only see the upper surface of the belt. So there is a part of the belt underneath the top layer that we cannot see, and that introduces a relatively big error. In order to solve that, we counted with the collaboration of UPM. We did a lot of experiments, measuring manually a lot of samples in order to adjust the results of this service. And actually, we managed to improve a lot the first results that we obtained. Having said that, this is the graph or the dashboard that represents all this information. And we have on the top part the size distribution of the material, but as a percentage. So what percentage of material is below a certain size threshold. In the lower part, we have the information in a similar way. In this case, by number of fragments for each size segment. Sorry. As I mentioned, it's a strategy. For each strategy, we have the longest side, the shortest side, and the area. We observe that the best results are obtained with the shortest side, which makes sense because the way they do it, when they measure this granulometry manually, they are using sieves to filter the rocks. So a rock fits through the sieve through its shortest side. So it makes sense that the most accurate, the most accurate way is the shortest side. And as before, it can be filtered to focus it on a certain moment in time. All right. As I've been mentioning throughout the presentation, we are detecting anomalous events, and all these events are gathered together in the Power BI dashboard, in this Power BI dashboard that we have here, in which we can see the date of a certain event, the service it corresponds to, a description. For example, if it's a grain size event, we can distinguish whether it's because there are too much material in the over 40 or in the over 25, and the priority. And we can also filter by the service that we want to focus on. All right. So now changing a bit the topic, I wanted to talk about MetaQuery. MetaQuery, it's a document search engine, so to say, that finds a convenient way to locate information within documents. It differs from traditional keyword-based models in that you can directly type a question the way you would ask another person. So as we can see in the example, we are asking it, excuse my translation of French, but something like, what should you do if you get electrocuted? And the MetaQuery, instead of just giving you a document in which you have to search, it tells you an answer right away that we can see here. And it tells you should turn off the main switch before doing any kind of intervention. Besides this information, of course, it's going to provide the document where you can find that information. You can download it, and it also highlights the section within the document where you can find that. This service is based on the Mixtral model, which is a large language model. As I mentioned, it supports automatic summary and question answering. It's available in all the languages that are involved in the project. And it's integrated, meaning that it can access documents stored in the data lake in a private cloud such as SoundCloud, SharePoint, or Google Drive. And the last service is the forecast service. This service is thought of a service that takes information from different sources and provides some additional information. In this case, it's focused on giving an estimation of the consumption of water at the end of the year for a quarry, predicting when in the next days the energy is going to be cleanest, the energy used by the quarry, and also to determine the impact that the weather has in the production. This service has been deployed in Simpor, in Alenquer, which is in Lisbon. This service has several parts. On one hand, we have a sensor network that I will talk about more detail before. In the next slide. We have a sensor network that gathers data from the quarry itself. It's also integrating data from IPMA, which is the weather agency from Portugal, and OMIE, which is the electrical operator for the Iberian Peninsula. But it also gets data from the data lake, in concrete the production data. Data from the sensors goes through the IoT platform that was described by Sadek before and ends up in the data warehouse together with the other information, and then all that is consumed by the models, the forecast models. As I mentioned, I wanted to give an overview of the sensors that have been deployed in Alenquer. Here on the left-hand side, we can see a map of the quarry, and here we deployed 4 that sensors that we can see on the upper right corner. The left of them is a commercially available sensor, but I also wanted to highlight the fact that we developed 3 of the other ones, the one with the black background. We did them from scratch in our premises, in our offices, using components that are available off the shelf. Besides these sensors, we also deployed 2 pulse counters that are connected to the water meters in the quarry, and they measure the water consumption of the quarry at its point. And lastly, we installed an anemometer to have localized wind readings within the quarry. These sensors send their data using the LoRaWAN technology through a gateway also deployed in the quarry. And from there, through the Things network, a platform that's focused on managing this type of networks, from there it goes to the IoT platform that code is set up. And now we'll see the results of the different parts of the forecast service through the different dashboards. So the first one, as I mentioned, it had the goal of analyzing the water consumption, and it has different parts. Here in the map, we see the dust levels at different points in the quarry, wherever the dust sensors are deployed. And also weather information for the quarry. This is all local information, not retrieved from the internet, but from the sensors. We have the temperature along with the historical temperature, the same for the humidity and the wind. We can see both the direction and intensity. And this is the AI service itself. Here we measure the amount of water that's being consumed currently, which is determined by this arrow, but we can see the projection of water that's going to be consumed by the end of the year. We can see it's quite low because it's been raining a lot. So this water, which is mainly used for dust mitigation, the consumption hasn't been too high, although now that summer it starts, we'll see an increase in consumption. So we have the consumption at the end of the year, the moment where the limit, which for the quarry I didn't mention, but they have a 10,000 liters limit that they can't overpass for a given year. So we'll see when that limit will be reached if we are consuming water at the current rate. In this case, it's very low, so it's going to be in 2 years, it's no worry. And on the right-hand side, we have a similar information. We see the current consumption up to here. And from that point, from today's on, or let's say, we can see an estimation, the regression curve for the consumption for the rest of the year. And yeah, I think that's more or less it. We can also filter it timely. That's a common topic for all dashboards. All right, so that's the first service. The second one is related to energy. This one, as I mentioned before, its goal is to determine when the energy that the quarry uses, it's the cleanest. And we are taking the assumption that whenever the price of the energy is lowest, that means that the main source of energy is indeed clean energy. So here we see, that's just a representation of the historical prices, electricity prices in Portugal. And then the output of the service itself, we can see on the right-hand side, which is simply a prediction of the price for each hour and for the coming 5 days. It depends on the predictions that are available for the weather. So if I'm the quarry operator and I need to plan a stop, for example, here, the 29th of April, I will look at the graph. I will see when the price is supposed to be higher, which is over here and over here. And I can plan a stop in one of those time ranges. So yeah, so I'm going to save more because I'm going to focus my production in a time frame that's where the energy is cleanest and therefore cheaper. And yeah, that's the output of the model. And again, it can be filtered by time. And last but not least, the production model aims at determining the potential maximum production for a given day, taking into account the weather conditions. And here simply we see also the production history. This is taken from the data lake. We see that the production for each day, and then the output of the service. Here we see for the coming 5 days, the potential maximum production in the quarry. So we see, for example, for today was the 23rd or the 24th for tomorrow, we see that given the current weather conditions, because the main impact in this service is the weather conditions, given the current weather prediction, so to say, and the maximum production is going to be around 50%. That happens for all the coming days. And I think that's it. Again, it can be filtered, and we can select to see the actual production. We can filter by end product. And I think that's it. I'll give the floor to José Luis Blanco, and then I'll be happy to answer your questions after that.
Thank you, Javier. As you just said, I'm José Luis Blanco. I'm Associate Professor on AI at Universidad Politécnica de Madrid, which happens to be the top-ranking largest university in Spain for engineering studies. Our work has been in basically 2 services, AI services. The first one is about anomaly detection. I believe everyone here knows that sound, noise, vibrations kind of serve as proxies of issues going on, so to say. What this service is about is the productization of a continuous monitoring system that can actually operate at the edge, can actually check what is going on whatever the device is, regardless of the context, situation, scenario, whatever, and then fire out alarms, alerts, depending on the kind of things that are happening or the issues or whatever we want to do with that. Actually, Cesar, you mentioned this before. We are one of those services that lacked historical data to be developed. That was something from the very first day, and that's something we actually want to thank all the sites involved in this project, because all of them have been involved with us in collecting audio records, which has been a tough task, but already have collected 300 hours of data that we can be using, actually. The idea behind this service is essentially we have these edge nodes that actually predict each of the individual components, even if they are outside in the open real world of a quarry, which you already know it's quite complex, and take their own decisions, decide whether this is relevant or not so relevant, or if this specific element that they are seeing should be pushed into a specific cloud component that is able to classify specific AI complex events. So do you have an idea? Definitely the kind of sound, noise, I would say, that we have on a query is kind of noisy, as you can see here. But what we actually do is, based on AI, build models that say, okay, this may be complex, but still normal. We want to check what is abnormal, or actually where things drift from normal stuff. And we work on that. That's essentially the idea. Fortunately for us, this has been deployed and is working. But to be all honest with you, we haven't found any kind of real big alerts throughout the project. So congratulations to the sites. But from our perspective, there's still work to be done, because we still have to collect more data to relate all these events that we are seeing with further things that go on the query. That's why we believe throughout this project, we have gone from TRL 0, no one knew how to do this, to 4, but we still need to push this a little bit further to become a real final product. But still, we have managed to build on Power BI some dashboards that kind of summarize what's going on, which essentially means we can have alerts on the different components that we have and check whether, first, this edge component is still working, which is not so easy all the time, and as well, whether it is firing out alerts or not, and computing how many of those are. We don't just have simple alerts, but alarms, depending on the degree of certainty that we have on how challenging the situation might be. As said, we have had alerts. We haven't had real alarms up to now. That being said, we are actually foreseeing how this technology can go beyond queries. And we are already actually deploying this technology in our own servers for the AI, because they still sound and vibrate and have things going on. What you see here is actually the component that we've built for this project, for the DigiEcoQuarry, that has been deployed in our own server at the university to check that things are operating correctly. Maybe you don't imagine this, but that thing still sounds a lot, buzzes a lot, vibrates a lot, and if things are going wrong, it does odd stuff. So it's kind of meaningful for us. That being said, well, that's the kind of audios that we see, completely different plot that we had before, but we still somehow see things here. That's essentially the kind of anomaly. The technology that we built allows us to operate whatever the situation is, however complex it might be, we still can detect those anomalies. Our goal now that we have a data set is basically, and we have completed a two-stage architecture for the whole service, is to show up what this technology can do. Still, as said, it still needs to continue building the technology and productizing kind of the background of the backend that is processing the whole stuff. But that's essentially how this service is now already operating, and as said, productized on our own servers. At a completely different scale and situation is the other service, the stockpile volume calculation, which we understand should be around TRL 6. And this, I believe you've all heard about it. Smartphone, collect data, compute, stockpile volume, go. That's the whole thing about this model. We have already been working not just on computing stuff, so we get this kind of representations in computing the volumes, reconstructing them, estimating volumes, so on, but as well in the user experience, which we believe is critical for this use case. It's not just about you collecting video, it's you being able to collect your own data with your own smartphone, and then having your own data to manage about how the query is actually operating. This brings us to an interesting situation. We have already built a productized app. Some of the queries, I believe actually all of the queries, have experienced our data acquisition app, which was kind of an instrument. Now we actually have an app that is meant for commercialization, for demoing, for showing up, which is not just about collecting data, but as well as logging into it, defining roles, defining the experience, checking the historical data, the whole stuff, all connected to the different infrastructures that we have in the DigiEcoQuarry. Apart from that, once again, we didn't have data on stockpiles, that's the truth. So we had not just gathered several data sets on the different sites, but we have also built up one that is synthetic, so that can be compared with other technologies. By summer this year, we will be publishing a contribution comparing our own technology to the models that had been designed in 2025 by Meta and Google to check that actually our computation of volume is much, much better, and much more importantly, is productized for an industry. It's not just for people playing around with the models. It's about actually using it from the smartphone and getting your solution, which is something that has not been done before. All in all, we have reconstructed up to 53 stockpiles, which has been a challenge. Once again, thanks to all the sites, because it has been complicated. Their operators have collected for us the information, so thank you for taking the time to use the app and tell us how to improve on it, which has already as well been an experience. And they have already described to us the whole experience, how this should be used, how the actual operators and the managers and the business managers want to work with it. And that has been a huge challenge that has allowed us to reach TRL 6. We actually understand that in the coming months, not more than 1 year, we should be able to scale as a product and go for TRL 8, which basically means that we do have dashboards, so we can represent the data. We have followed the same approach as in the same other services in DigiEcoQuarry, where we can not just have the different sites, but specifically information on how the piles are changing on their information, whether you have more info or less of that. The models that we built are also capable of measuring the error, which is something that is not so typical in AI, but for us, based on your intel, has been a major thing to do. So we can do all of that, and managers can have their own data whenever they want it, just through their smartphone. Please remember that thing. Next goal, let's go for TRL 8. Let's go for larger stockpiles. The larger, the better, we guess. Now, in all honesty, the whole project is basically productized. What we're gonna do now is to scale with sites, scale with people using this. So we expect to launch actually the app in the coming months directly for people to use it and see how this goes on from here on. So looking forward for new challenges on this stockpile volume. Whatever your pile is, please contact us and just use it. That's all from my side. Thank you.